Okay, we are here today to have a seminar on mineral physics from Dr. Abby Kavner from the University of California at Los Angeles. And she's going to kind of give us a background information about what is the science of mineral physics, how it connects to physics, chemistry, and geology. So definitely please take it away, Dr. Kavner.
Great, thank you. Looking forward. This is what a treat.
Thank you for joining us.
Okay, so I'm looking forward to sharing a slice of my research life with you. Do you see my rusty globe now?
No, we still see you.
Okay, let's try one more. How about now?
We see there's the rusty globe.
Good, okay, great, fabulous. Okay, super. So what I'll do is I'll scroll through the slides, and I think I can get back and forth. I actually have some show and tell to share today also. So but I'm looking forward to sharing a slice of my research and science life with you. So Will asked me to say a few words about the path that I took to be a scientist. So recognizing that there's no single roadmap for everybody, I just wanted to show you a top-down view of my combination personal and professional trajectory. So you see the roadmap?
Yes.
Okay, great. So yeah, so I knew I wanted to be a scientist ever since I was a little kid, and so I studied engineering at Northwestern. I grew up on the East Coast, in the country, in the Hudson Valley. And then I went right to graduate school where I did a master's in materials engineering at Berkeley, at Cal. And then I switched to geophysics, mostly because I went on a field trip, a geology field trip. I had an opportunity to drive a van across California, and I realized that geology was just material science applied to the earth. And I really fell in love of that combination of asking the earth questions about its secrets and also doing the science. So the same summer that I graduated, I got married, so there's been a personal trajectory also, and I went right to Princeton, where I had a postdoctoral fellowship in the geoscience department there. We had a son, Jim and I had a son named Emmett in '99. And while I was a postdoc, and then I did a second postdoctoral stint at Lamont Doherty Earth Observatory, which is Columbia University's Earth Science Research Center. And I've been at UCLA since 2002. I was tenured in 2008, and currently coming up for a full professor right now. It's been a fun trajectory. There's a huge world to explore, and I've really loved I've really enjoyed honing my skills at becoming a scientist. So I can hear you if you ask any questions, right?
Yes.
Okay, great. Good. Just making sure. Fabulous. Okay, so here's a picture of the anatomy of the Earth. So if we think about it from the inside out, there's a solid steel core at the center. And I say steel because we're pretty sure it's not pure iron, but it's actually some combination of iron and some other elements mixed in there. And it's surrounded by a liquid iron steel, and the movements of those liquid irons actually create a dynamo, a electromagnetic dynamo action that creates the magnetic field of the Earth. The largest volume of the Earth consists of the rocky mantle. It's basically a giant green rock. I'll be able to show you afterwards, so we don't have to switch back and forth. I'll be able to show you what it looks like, or what we think it looks like, because we actually don't really have a way to directly get down there. And even though that mantle is rocky, we know that it convects on a very slow 100 million year type time scale. So it's heated from below, convex in the mantle, and then the surface, the crust that we live on, is actually a very thin layer, especially on this scale. And you can think of the plate tectonics, the movements of the the surface, the crust, as that two-dimensional manifestation of the three-dimensional convection that happens within the bulk of the Earth. So that's kind of an anatomy picture, but what we'll really talk about in this talk is the physiology, or how the Earth does what it does and why it's so interesting and important. But before I turn to that, I'd like to address the question that people coming from outside the Earth science always, the first question is, well, you've just told us the structure of the Earth, but how do we know that structure? And that's actually one of the joys of being an Earth and planetary scientist, is that we piece together like a giant scientific puzzle our knowledge of the Earth based on discrete and distinct levels or different lines of reasoning that we put together to form the best hypothesis, or our best picture of how of what the Earth consists of and how it works. So basically we have geophysical observations. So we have the gravity, moment of inertia, mechanical behavior of the planet, and as you'll see, actually seismology gives us some of our best geophysical constraints, and that tells us something about the structure of the internal of the Earth. And then to get a sense of what it's made of, we have geochemical arguments that I'll talk about in a little bit. What I do is I'm an earth material scientist. We're called mineral physicists or mineralogists, and what we do is we take the actual chemistry, the actual rocks and minerals that is our best guess of what the Earth is made out of, and we subject them to the very, very high pressure and temperature conditions that we think are relevant to the interior of the Earth, and then we measure their properties at those conditions and compare with what's observed geophysically. If it all holds together, then we make a consistent story, and that's our best guess of how the Earth works. So every time you feel an earthquake, and I think there have been some earthquakes in Arkansas recently, maybe minor ones. Have you guys felt earthquakes?
Yeah, we've had a couple due to fracking.
Right. They're local changes in the mechanical properties.
So we're near the New Madrid fault zone. So
right, of course. So one of the largest earthquakes in this in the country was in the New Madrid fault zone. So every time there's a really large earthquake, it sends acoustic waves. Okay, so these vibrations through the Earth, and if you have seismometers positioned, so measuring those vibrations positioned around the surface of the Earth, you can get the travel times of the waves as they're propagating through the Earth. And just like in a CAT scan, where you can do a tomography by measuring, X-ray transmission or acoustic waves at different parts of the body and invert that to form a three-dimensional image, geophysicists take the earthquake information, the travel times, and can invert that for the structure and the wave speeds of the interior of the Earth. There's also another interesting part of that, which is if the earthquake is large enough, so for example, like in that 2011 Japan Tohoku earthquake, if the earthquake has enough energy, it can actually excite the normal modes of the Earth. So like your musical instrument, right? When there's a lot of acoustic energy, you vibrate it and you hear the fundamental tones and the overtones, and that tells you something about the size and shape of your musical instrument, like your trumpet, as well as what it's made of. The same exact thing with the Earth. The normal modes of the Earth have fundamental frequencies that you can use to tell something about the structure and the structure of the Earth and its properties. So mostly from seismic information, and then also a little bit from our moment of inertia and mass and gravity constraints, we have a really good sense of the velocities of acoustic waves as they travel from the surface of the Earth to the interior. So here's shear waves and compressional waves as a function of depth. And you can see that they're on the order of tens of kilometers per second. So this is acoustic wave speeds through media. So it's like rocket ship type speeds. And then we also know the densities of material as we go down into the Earth. So the density of rock that's compressed is about 4 grams per cc. You can feel that. As we go down, the density increases significantly. And then the inner core, or as we go into the core, the densities get very high. So that density distribution is expressed as the moment of inertia, and that's typical for the terrestrial planets. All look relatively similar. But this just tells us about the physical properties. So the wave velocities have to do with the elastic properties and the density, but doesn't tell us anything about what's inside the Earth. So I mentioned before that the core is mostly iron, probably with some light element, and the rock that's on the surface is mostly a silicate rock. You can actually think of it as closed-packed oxygen ions, each with about a -2 charge, plugged up with silicon, magnesium, iron, and aluminum. Those are really the major elements through the Earth. And in fact, this quarter here at UCLA, I'm teaching mineralogy, and we go through those silicate rocks. But we're going to talk a little bit about the SiO6 unit, because deep in the Earth, that's the fundamental building block. It's our fundamental molecule that builds the minerals inside the Earth. And so its behavior, its physical behavior and chemical behavior are really important. So how do we know this? So how do we know the composition? So we know the composition indirectly, mostly through a series of arguments from cosmochemistry. So we have at our disposal, so we have meteorites collected. These are the oldest rocks in the solar system. They land on the surface of the Earth. It's hard to tell them apart from our normal Earth rocks, except for in places that there's a giant ice sheet, such as Antarctica, and we can go and pick these up from the surface there and collect them. And most of them are actually rocks, but if you do a radioactive dating on them, you'll find that they're some of the oldest rocks. In fact, they're usually around 4.5 billion years. Okay, so we have the meteorite and we understand their chemistry. Now, on the other hand, we also have our absorption and emission spectra from the sun. So if we look at the light of the sun, mostly it's a black body emitting at around 5,600 degrees Kelvin. But if we do a high-resolution spectral analysis, there are energy bands that are associated with the chemical fingerprint of the sun. So we know the composition of the sun. Now, we also know that the sun is over 99% of the total mass of the solar system. That is, almost the whole solar system is contained in the sun. The planets are just, even Jupiter, which is still less than 1% of the mass of the solar system. So the argument is that if it's in the sun, that the sun's chemistry represents the chemistry of the entire solar system. Well, it turns out that except for the very light elements like hydrogen and helium, and some of the other volatile elements that we think of as being very gassy, the composition of our rocky meteorites agrees almost exactly with the composition that we see in the spectra of the sun. And so this tells us that we think that the rocky materials, that the meteorites built the terrestrial planets, and that if we look at the composition of the meteorites, that gives us a pretty good first-order guess about what the composition is of the Earth. Now, of course, the details of that are very much in the field of geochemistry and cosmochemistry, and well, I will tell you that they like to yell at each other very loudly during our meetings, so there's a lot of arguments in the details. But generally, we do understand that there's a lot of oxygen, silicon, iron, magnesium, aluminum, calcium in the Earth. So we know what the raw building blocks of the materials are. So my job, and there are several hundred of us in the country and around the world of mineral physics, is to take these candidate materials, these oxides, silicates, iron-rich metals, and bring them to the conditions of the interior of the Earth, so that is very, very high pressures and very high temperatures, and measure their physical and chemical properties. So we measure their phase diagrams, at what temperature they melt at. We measure the density and how the density changes as we pressurize and how the density changes as we increase the temperature. So thermal expansion on the one hand, a compressibility on the other hand, and then the cross derivatives as we go down into a planet. We measure the elasticity, so we know not just the bulk sound velocity, but also shear velocities at those conditions. And then now we're getting into more complicated types of measurements, chemical reactions, and elemental distribution. So, for example, we have the metal core and we have the oxide or rocky mantle. How does iron distribute itself between those two phases? So these are all very active questions that we're asking in the field and making the measurements at extreme conditions to try to answer. Those are equilibrium properties, but remember the Earth is dynamic. We know that the mantle is convecting, so we're worried about diffusion. How do elements how do the chemical constituents of the Earth evolve as a function of time? How is the Earth formed, and where are we on its trajectory? To separate mantle from core and crust from mantle, we need to create a melt and then move a melt away, because chemical diffusion in the solid state is very slow. So we need to understand the viscosity of those melts, and that turns out to be a very difficult measurement. We were at the labs last weekend trying to make that measurement. Also, we need to understand electrical conductivity. So if we know that there's a magnetic field being generated in the middle of the Earth, but our rocky mantle is a partially conducting insulator, then our measurements of the magnetic field from the outside have to be filtered through an electrically conductive rock. And so we make those measurements at the high pressure and temperature conditions. And then the Earth is hot on the inside and it's cold, room temperature on the outside. And so today I'll talk a little bit about one of the specialties of our lab, which is measuring thermal conductivity. How does heat flow through materials? So how do we do these measurements? So in general, to make the measurements, the key parameter is that once you're down into the crust, just a little bit in from the surface, the pressures get extremely high, and the properties of materials change. So in order to be able to measure material properties, we have to bring materials to those high pressures. And the way we do that is by using an instrument called a diamond anvil cell. And that picture is my grad student, graduated in a few years ago, Matt Armentrout. He has a diamond anvil cell under a microscope. So we use microscopic pieces of rocks. To our eyes, they basically look like pieces of dust. And we actually squeeze them in a device between two diamonds. And these are gem quality quarter carat diamonds. And I'll show you some of these after the talk. And the diamonds they have a couple properties that are really useful to us. First of all, they're very hard, so we can apply a force, a large force, without breaking the diamonds, and the sample is small. So we're applying a large force over a small area. And remember, the definition of pressure is force per unit area. And you can always do better by decreasing your denominator. So we get very, very high pressures by using large forces and then low and then small areas. Now the diamonds are also transparent to almost all light. So not only can we see our samples through the microscope, like Matt's looking on the left, but we can also shine an X-ray into our sample and make a measurement of the diffraction pattern, the structure. And so you can see a diffraction pattern at the right of, I think this is a cobalt oxide at high pressures and high temperatures inside the diamond anvil cell. So we're looking at X-ray diffraction, which tells us not only about the phase stability, but also something about its density. Now, to heat up the sample, we couple in an infrared laser that is absorbed by the sample, and then we can simultaneously see our samples at high pressures and high temperatures with the X-ray. So we can use this diamond cell to replicate the conditions at high pressures and high temperatures. Oh, by the way, my Twitter notices are popping up, so that's a great way to ask me questions while I'm giving my talk. If I see them, I catch them, I can try to respond. That's pretty cool. Anyway, you can see them also. Okay, so my research group at UCLA, I've been here for 12 years, and our job, among, of course, our collaborators and other parallel mineral physics groups, are to measure material properties, so equilibrium properties, transport properties, physical and chemical properties of materials that determine the chemical and physical evolution of the Earth and the planets. So there's a picture of us. It looks like we're at the Advanced Light Source up in Berkeley, California, doing some synchrotron-based experiments where we can get a very intense beam and make some measurements. So that's a general introduction, but let's back off and address our big question. Our big question really is what makes the Earth, or what makes planets so interesting? And as we're discovering many, many other planetary systems in neighboring solar systems or within our vicinity, we want to be able to ask, how do the planetary systems work? And if we were to choose where we might send a probe or where we might target a visit, what makes an interesting planet? Well, one of the ways to answer the question is an interesting planet for us would be one that supports life. So we can ask, what is it about the Earth that gives it the environment that can support a habitable a life, that allows life to evolve and form? What makes our planet interesting? And we all, in our research group, address certain aspects of that question. So, for example, Matt, and you saw his picture before, he might say, well, the Earth is really interesting because it's out of chemical equilibrium. And that is that you have this giant, massive iron core at the center, and it's in contact with an oxide surrounding, and then that's in contact with a water-based crust. So the chemical reactions actually can generate energy enough to power life. So Matt's research was to look specifically at that core mantle chemical interactions and ask about whether or not it's in equilibrium and how it might attain an equilibrium. My current student, Sarah, she might say, well, Earth is able to support life because of the volatile content, because of the carbon recycling throughout the Earth, and because of the water cycling throughout the Earth. We can't have a planet with life without carbon and water that have a certain cycles within different parts of the Earth. And so her research is looking specifically at carbon and how carbon-based phases are stable at the high pressures and temperatures in the Earth, asking the question, how much carbon is stored in that big, large, volume of mantle part of the planet? Now in our group, we're not only earth scientists, we're also material scientists. So we have collaborators in the chemistry department who take what we understand about measuring properties of materials at these extreme conditions and use them to synthesize materials that might have particular properties. In our case, we're very interested in ultra-hard materials that can be used in a practical way as cutting tools or grinding abrasive tools. And in fact, you should know this. If you decide to study mineral physics, high-pressure mineral physics, if you go on to graduate school and study, that's actually one of the places where many of our PhDs get employment, looking at the properties of super abrasives or ultra-hard materials. So they're important for industry as well. Well, on the bottom here, you see that our group is sponsored by a range of federal funding from the Department of Energy, which is interested in carbon cycling, of course, and then markers for chemical reactions inside the Earth, from the National Science Foundation, which supports our basic big questions in the Earth, what makes the Earth so interesting, and then also the National Nuclear Security Administration, which supports some of our material science-based research on the properties of materials at high pressures and temperatures. And as we go into the Q&A, I'm happy to answer questions that you might have about the sources of those fundings and what their specific interests and requirements are. So we all are interested in the Earth in my research group because the Earth is dynamic. It's not static. And so we showed the anatomy of the Earth before with its rocky mantle, liquid iron core, and solid inner core. But actually, the Earth is continually evolving. The mantle is convecting. The crust of the Earth is moving. You're creating new crust by partially melting the mantle near the surface. And you're actually, as the crust cools and becomes denser, it actually becomes denser than the ambient mantle and subducts back down. So there's large-scale cycling that's taking place in this dynamic Earth. And so for the rest of the talk, what I'd like to do is talk about one of the research projects that my group specializes in, and that is measuring that heat flow, asking how does the heat from the Earth evolve? What's the thermal budget of the Earth, and how is the heat flowing? I want to do this project because not only is it one of the fundamental questions that we have about the Earth, that is what's powering the dynamics of the Earth from a fundamental level, but it also has some really, really nice physics. So we really get to look deeply at the physics of materials as we're asking this question. I also like this project because it's a combination experiment theory result that's been done by two members of my group. So Emma Rainey, current graduate student who's actually defending her dissertation in 2 weeks. She's the experimentalist and has also supplemented that work with modeling. And then a few years ago, I had a wonderful time with a visiting postdoctoral researcher, Xiaoli Tang, who's a physicist from her expertise is doing first principles calculations of the microscopic heat flow behavior in materials, and so what I'll show you are some of the results that we've put together to tell us more about the dynamics of the Earth. So, when I went through the anatomy of the Earth before, I was able to show you a little bit about the composition, a lot about the wave speeds, and a lot about the density. But I don't know if you noticed, but I didn't really show you a temperature. And the truth is that we actually don't know the temperature profile of the Earth very well. It's highly, highly uncertain. So if we're looking at the thermal state of the Earth, we want to ask first, well, what's the temperature of the Earth look like from the inside to the outside? This is a big question in our field. Many of us are working on it. But as it turns out, we rely on fixed points to get these temperatures. We know the average temperature of the surface is approximately room temperature, around 300 K. It's approximately the temperature of the oceans. And the other fixed point in the Earth is set by the boundary between the molten outer core and the solid inner core. And that one's really, really interesting because temperature goes up as you go into the Earth, but as you take solid iron and increase the temperature, it should melt. So the fact that we have a solid iron in the inner core and a liquid iron on the outer core tells you that that boundary defines the melting temperature of the iron alloy at that pressure. So if we were to take our diamond anvil cell, load it with iron, laser heat it, and measure the melting temperature of iron, we would have the temperature at that inner core, outer core boundary, and therefore pretty much through the entire core of the Earth. Unfortunately, that's one of the most difficult measurements that people can make at high pressures and temperatures. So we think it's around 6,000 degrees K, but it's uncertain almost at the 20% level. So that means that we don't know the temperatures at the inside of the Earth very well. So what other constraints do we have? Okay, well, first, before I go to the other constraints, here's another picture of the temperature profile in the Earth showing the inner core, outer core are fixed points. We know the temperature at the surface. This iron melting temperature sets the points here. We know that the outer core is convecting. So if everything were uniform pressure, it would be an isotherm. But because pressure is increasing across that convection, we actually have temperature increasing a little bit. In the upper mantle, in the mantle, we also have convection, and if it were a constant pressure, it would be an isotherm, but because pressure is increasing, temperature is also increasing. That shape of that curve is called an adiabat, but it's a result of the thermodynamic behavior of materials. Just like if you squeeze a gas, as you increase the pressure of a gas holding everything else constant, the temperature will increase. The same thing happens with rocks. The different law, different empirical parameters, but it's the same basic behavior. We actually know that there are phase transformations. The silica rocks undergo a series of transformations in the upper mantle, and we have relatively good constraints on what those temperatures and pressures are, so that gives us another series of fixed points. But the important point is this is uncertain, this iron melting temperature at the inner core outer core boundary, and that makes the temperature drop at the outer core mantle boundary, the thermal boundary, major thermal boundary of the Earth, highly, highly uncertain. So what other constraints can we look for? The next constraint comes from the surface heat flux. So as we can measure in a series of boreholes, the first ones were in mines in some areas on the continents, but also in the ocean floor. As we drill down, we can measure the temperature as it increases. If we assume that the surface of the Earth is a thermal boundary layer, which we now assume, we can actually take these borehole measurements and plot out the heat flux as a function of area on the surface. So here's our map of heat flux in milliwatts per meter squared. And you can see this is one view of the Earth's plate tectonics. We have very, very high heat flow concentrated in these linear boundaries where new ocean plate is being formed. And the continents, so here's North America up here, here's Arkansas right down in here, the continents have relatively low heat flux. They're nice, thick thermal boundary layers. And we can integrate our measurements and get a total surface heat flow coming out from the interior of the Earth of on the order of between 45 and 50 terawatts. And this number is relatively well accepted. By the way, if we think about how much energy is beating down on the Earth from the sun, the solar heating from above, that is orders of magnitude larger than the heat flow coming from the Earth. So life on the surface is powered by the sun, by solar energy. And so these heat budgets really exist at different scales. But this surface heat flow is the evolution of the Earth's internal heat as it's coming through the surface. So what we have is a giant accounting problem. So we have the thermal state of the Earth, some combination of the Earth cooling from its initial high temperature, and some contribution from leftover radioactive elements. As they're decaying, they let off heat. And so we know there's uranium, and there's thorium, and potassium, and some other radiogenic elements. And this whole budget has to equal our total observation of heat from the surface of the Earth of between 45 and 50 terawatts. Now, what are our constraints? So just like we have a budget, we have to say where is our heat coming from. So the contribution from radioactivity is in the Earth's crust is known pretty well. Actually, uranium and thorium, potassium like to concentrate in the continents, and so we know that number, and we know how much heat we require to cross the core mantle boundary so that we can power that geomagnetic field. We can give that dynamo enough power to create the magnetic field, and modeling tells us that. So these two are relatively well-known constraints, and the rest are less known. So we have the radiogenic contribution from the crust, but the rest of the budget of heat-producing elements is actually not well known in the Earth. So it could be almost all concentrated in the crust, or we could have almost half the total heat budget be taken up by radiogenic, by the radioactive elements. Now, we require 4 terawatts to cross the core mantle boundary in order to observe our magnetic field, but there could be far more, and there could be far less. So these are typical constraints from old data and incomplete data. And the problem with this data is that a colleague of mine, Bruce Buffett, so he's a professor at Berkeley, he took these values, and what happened was when he back calculates if these are the current heat production through the Earth, and there's 10 terawatts crossing from the core to the mantle, if you back calculate through time, you get way too high temperatures towards back in geologic time, so 2 or 3 billion years ago. And in fact, the inner core must have been formed only very recently within geologic time, so over in the past billion years. So when the current numbers are being used, there's a problem with the heat flow through the Earth. And that problem comes across because of this thermal boundary layer from the core to the mantle. So you can think of the core as having a high thermal conductivity. Heat can flow relatively easily. And you can think of the mantle, this rock, as an insulating blanket onto the core. And so the question is how much heat does the mantle permit to extract from the core? We need to permit enough so that the dynamo is driven in the core. But if we permit too much heat to flow, then as we go back in time, our core becomes a giant hot plasma, and it's just not physical in terms of our understanding of the Earth. So the reason that these values are uncertain is because the thermal boundary layer is governed by a combination of the material property of thermal conductivity and this temperature gradient. And as I said before, the temperature at the core is uncertain, the temperature at the mantle side is uncertain, and the thickness of that thermal boundary layer is also uncertain. So I have a length scale of around 100, 150 kilometers, but it's uncertain to the 50% level, and it could be varying in space. The thermal conductivity, which is the material property that governs how insulating the blanket is also uncertain to within the 50% level. So that means our current heat from the core to the mantle is uncertain by a factor of 2. And this means that we don't understand the thermal evolution of the Earth. So here's the problem. If the thermal conductivity is too low, okay, so if the mantle is too good of an insulator, then the core is very hot, it's difficult to generate the magnetic field, and we might even be melting the lower mantle. And our seismology tells us that we don't have large-scale melts in the lower mantle. Waves can tell the difference between solids and liquids, and the mantle is definitely solid. Now, if the thermal conductivity is too high, we're fine now for our budget of the heat flow, but as we go back in geologic time, the core becomes much, much too hot, too recent in geologic time. The thermal conductivity is also important in detail to determine exactly the scale and mechanism of the convection in the mantle. So we really want to understand this number and how it behaves. Okay, so let's take a look at what we did in our group. So the first part was Xiaoli Tang's part, and she did the theory. So what she did was a series of ab initio, so this is first principles physics calculations that directly calculate, using the Boltzmann transport theory, the lattice thermal conductivity. So these are the microscopic scale vibrations in the crystals that make up the mantle, and it's a crystal of a mineral called bridgemanite. And this thermal conductivity is a product of the heat capacity, so how much heat is carried by the crystal, times the phonon group velocity, which you can think of as the acoustic waves at the microscopic scale and their velocities through the sample, and the phonon lifetime. So the phonon lifetime is a scattering time scale. How long do the phonons, these waves, propagate before they scatter and exchange this heat? So this is a very, very simple overview of what ended up being a very complicated and time-costly, computationally costly calculation. But we have 3 things: heat capacity, phonon group velocity, phonon lifetime. I'm not going to be able to go through this in extreme detail, but it was published this past year. And actually, the theory was published in a series of papers by Xiaoli Tang and her PhD advisor, J.J. Dong. But you can see we have measurements of the heat capacity at high pressures and temperatures. And the heat capacity becomes approximately constant at high temperatures, as we know, and there's not a large pressure effect. There's a phonon group velocity, so this is really one of the hearts of the calculations. So we're measuring the phonon dispersion curves. Those of you who've taken solid-state physics in the group, are there any?
We don't have a course for that. We're going to try to get that on the books as a rotating.
Okay. Excellent. When you do, you'll learn how to calculate just one of those curves for the very, very simplest lattices. This is a really complicated calculation, but it really is just thermal energy vibrating through crystals. crystals. So this is material science and condensed matter physics. And then the last one, which is the heart. Well, if the group velocities is the heart of the calculation, then the phonon lifetime is the soul of the calculation. So this is the very special part of the theory that Xiaoli and her advisor JJ brought to the table, which is measuring these very difficult transport scattering parts of the measurements. And so the scattering time scales are on the order of picoseconds. The length scales are very, very small, much, much smaller than the grain size. And we put all of this information together in three-dimensional space, and what Xiaoli calculates is a thermal conductivity. So this is a number of value as a function of pressure at different temperature contours. So this is the calculation for the pure mantle material. If the mantle were a gem quality magnesium silicate bridgmanite, that's the name of the mineral that most of our mantle is made out of. So you can see the comparisons between the calculation and some of the measurements. You can see also that the measurements are mostly at room temperature, but to be relevant to the Earth, we want the measurements and calculations down here at very, very high temperatures and high pressures. Okay, so that's the results of the theory. Okay, as we pointed out, the measurements are down here in a low temperature range, going up towards high pressures with some recent measurements especially, but the geotherm, which is our temperature throughout the Earth, is at much high temperatures. So this is where we want to be when we make measurements. Okay, so the measured values that you saw before, they're all at low temperatures, and they're also very, very scattered. So one of the reasons that there's a large uncertainty in our understanding of thermal conductivity is that we don't have a very good series of measurements. So this is where my student Emma Rainey came in with her experiment and model. And so we're doing the experiments using laser heating in the diamond anvil cell, and we can measure the temperature of the material and the temperature distribution in two-dimensional space. That temperature, so when we use a laser to heat the sample and then measure the temperature, it's a function of a lot of different things. So it's a function of how much heat is absorbed by the sample from the laser, but that distribution is also a function of the thermal conductivity of the sample. So if we model the heat flow behavior in the diamond anvil cell really well, we can actually make the measurements, compare with the models, and extract the thermal conductivity as a function of pressure. So if we make a series of measurements of temperature, as we increase the amount of laser power going into the sample, we get a curve. And the slope of that curve and the position of the curve is related, all other things being held constant, to the material property, to the thermal conductivity. So this is what those models, temperature versus power, look like, and then this is what our measurements for this bridgmanite type material show us. So you can see that at low pressure and at high pressure, we are actually changing the values of the temperature versus laser power curve. When we take all of that information and put it together, and so actually there's a series of data that look like these temperature versus laser power, we combine it, and what we measure is a slope. We can't measure an absolute value very accurately, but we can measure an accurate pressure dependence of the thermal conductivity. So here's this measured slope, thermal conductivity as a function of pressure, with the error bars that of course increase. And these are measurements that are created at high pressures and temperatures. Now what we do is we combine this pressure dependence with our theoretical calculation, and in the end we come up with a measurement of the thermal conductivity as a function of depth throughout the Earth. Here's a reminder. So this is a picture showing all of the trade-offs. On the x-axis, I have our thermal conductivity across the core mantle boundary. On the y-axis, I have my temperature gradient. Remember, this is also very uncertain. The right-hand axis shows how if we vary the thickness of the thermal boundary layer as we vary assumptions in what the temperature is at the core or what the temperature is at the mantle, will create different estimates of this temperature gradient. But nominally, it's between these two horizontal dashed lines. The old estimates for thermal conductivity of the mantle were very broad. And you can see by the contours, and this is just contouring the total amount of heat that crosses the core mantle boundary, the previous estimates permitted everything from below 4 terawatts to above 25 terawatts. So it permitted the whole range outside the geochemical and geophysical constraints. With these new calculations and measurements, we actually have our new estimates for the core mantle boundary thermal conductivity. And you can see that our estimates suggest that the mantle is far more of an insulating blanket than had been previously thought. So what that suggests is that if we have along with this came new values for the core mantle boundary temperature drop, that we actually suggest that we have relatively low heat flux across the core mantle boundary. That instead of permitting 10 to 15 to 20 terawatts, we seem to permit 4 or 5 or 6 terawatts across that core mantle boundary. So now our accounting looks like this. We have a new core mantle boundary heat flow that's lower than what we thought. And there are many, many different ways to accommodate it. But one way is to create some additional layering, thermal boundary layer in the mantle at one of the other phase transformations. Another way to account for it is to have a higher budget of radiogenic, radioactive materials in the Earth, especially in the core. And then a third way is to allow a variable thickness of our thermal boundary layer. And in fact, that's the best idea, is that the core mantle boundary layer is mostly insulating, but has patches of high thermal conductivity where we have a downwelling slab, and thus making the thermal boundary layer thin and allowing more heat to go. So just like that picture that we saw before of the surface of the Earth, where we have concentrated areas of high heat flow and low heat flow, that's the emerging picture of the core mantle boundary, is that we have a two-dimensional patchiness, where mostly the mantle is thermally insulating, but in certain areas we're actually allowing much of the heat to escape in concentrated areas. So our new low thermal conductivity fixes some of the problems in back extrapolating temperatures. It allows the inner core to form early, and it allows the temperatures of the mantle to be, of the core to be reasonable as we go back in geologic history. The thermal conductivity that we determine is roughly constant. It has very weak pressure dependence, and as it turns out, a weak temperature dependence as well. And that makes it really, really nice for those who want to model convection. So it's a very simply behaved physical property for Earth's mantle. And then our best estimate is that the core mantle boundary is mostly insulating with patches of high conductivity. So very similar observations at the core mantle boundary with what we see at the surface of the Earth. So we predict an extremely dynamic, varied place at the core mantle boundary with dynamics that might be just as interesting as the plate tectonics that we see at the surface. So that's my heat flow story and a little bit of some of the summary of what we do in our research group and the trajectory that I've taken. And at this point, I'm happy to answer any questions, hear your comments and ideas, and chat for a while. Well, thanks.
Well, thank you very much. Let's give our speaker a round of applause. All right, you guys have any questions?
Can you say a bit more about your funding sources and what their motivation is for funding your research?
I'm sorry, there was a little bit of garble. Can you repeat that?
Yeah, so you mentioned earlier about your funding sources and that they each had specific motivations for funding your research.
That's right, absolutely.
Can you
Okay.
more
So the question is about the funding sources and what are their interests in funding this research. So the National Science Foundation funds basic research, and we as a scientific community, we get together and tell our National Science Foundation what the important things, the important questions are. So that's a wonderful way to do science. It's competitive, it's difficult to get a proposal funded, but it does come from the grassroots. Scientists do get together, and it is a true merit system. Wonderful, wonderful science is funded. There's lots of wonderful science that isn't. So the National Science Foundation is a great organization. I mean, they're all wonderful organizations. NASA, which I have been funded from previously, Department of Energy, where I have some funding, and the National Nuclear Security Administration are different flavors. Their scientific and engineering mission is top-down. So there's a Secretary of Energy who's in charge of what the priorities are for the Department of Energy. And their interests are securing our country's energy stability for the future. So, so a combination of resources and then also environmental mess-ups that we create while making sure that we optimize the resources. So, carbon cycling falls under Department of Energy. Measuring how we monitor contamination through the depths of the earth also falls under Department of Energy. You mentioned fracking before. So how does fluid flow through rocks at high pressures and temperatures? What's the combination mechanical processes and chemical processes that govern that? Those are the types of questions that are funded by the earth science part of Department of Energy. There are also funding for physics and chemistry from Department of Energy. So the National Nuclear Security Administration is a relatively new program that exists to monitor our nuclear safety. Part of the stewardship of our nuclear weapons program is ensuring that we still have the technology to verify and test devices, but we're not allowed to test devices. So we use computational approaches to model nuclear devices. And what we can offer, what I can offer as a scientist, are measurements of high pressure, high temperature behavior of materials that we can use either directly in a model, or we can lay out systematics so that we understand material properties generally as a function of high pressures and temperatures, and these can be used in models for nuclear devices. So that's where that funding comes from. It's actually a wonderful program that funds graduate student support specifically, and the idea is to train the next generation of students who will then go and work in the national labs.
We've got a question via Twitter here from Black Physicists. What are the prospects of doing some kind of thermal tomography experiment of the core mantle boundary?
That's a great question. So we have really, really tantalizing seismology results from everywhere in the Earth, but core mantle boundary. As our seismometers are starting to get better and better at recognizing very broadband, different seismic energy phases, we're getting high-resolution pictures of the acoustic anisotropy in the Earth. So patches where the wave speeds are particularly fast, patches where they're particularly slow, patches where the seismic wave speeds are much faster in one direction or the other. It turns out that the lower mantle, the convecting part is relatively homogeneous, but at the core mantle boundary, there's all sorts of fascinating structures, including places where there's reflecting energy, including places where there's large anisotropies, and then these large, low-velocity, high-density provinces that appear to be stable at the base of the mantle. So how do we interpret those in terms of temperature versus chemistry versus dynamics? Well, that's an active area of research. And so we need people who both understand the geophysics, the wave speed, the seismology, as well as understand the mineral physics. How do the materials behave? And again, we put together the puzzle by connecting those different lines of evidence. So that's an active area of research. But there's lots of great observations out there. We just don't understand why.
All right, John, you got a question?
Yes. First off, I want to say, awesome poster. That's hilarious. We're just laughing at that.
T-Rex.
Yeah.
It's from my Berkeley days. That's from my Berkeley days.
But my question relates to your Kavner equation.
Mm-hmm.
I was wondering, I assume the 1/3 has to do with the directional probability.
Yes.
How does that affect your overall comparison for measurement?
Okay, so the calculation ends up being a bulk calculation, and the real, well, I mean, there's so many approximations there, but some of the really important ones are the fact that we're doing this calculation for a pure gem quality magnesium silicate with no iron, with no dirty other phases, with no grain boundaries, with no defects. So the calculations are done on an ultra pure material. That's one reason that we interpret those calculations as an upper bound. Impurities, adding iron, adding a second phase, almost always tends to lower the thermal conductivity. So, for example, diamond, pure, pristine diamond has some of the highest thermal conductivity of any material. When you add an impurity into the diamond, it always lowers the thermal conductivity.
Okay, cool. When we looked at your website, you've got some interesting text in a big red box on several pages involving opportunities for students.
Yes.
Could you share what are some opportunities and how might students apply for those opportunities?
Sure, absolutely. So I tried to give you a sense of the projects that students in my research group are working on. One of the things you might have noticed is we all work on different projects. So earth science, especially what we do, mineral physics, is a great opportunity for a physicist who has some knowledge of laboratory work. So I like to take students who have some experience either working in a laboratory or working with their hands. So if you like to take apart your car and put it back together, that's a great experience for an experimentalist, someone who's comfortable playing with things and trying to make measurements. The National Science Foundation funding that I have is usually very flexible. So if students have a particular interest, I'm usually able to accommodate that interest as long as it's in the general range of understanding material properties at extreme conditions. We do a lot of our experiments here at UCLA, so we do spectroscopy experiments at high pressures and temperatures. We can do optical measurements. I do some isotope geochemistry measurements too to look at phase distribution. That's more of a chemistry question, so I didn't really talk about it here. And then we do a lot of our experiments at these large-scale synchrotron facilities. So we travel quarterly almost, so a few times every year. We get 3 days of very, very concentrated experimental time at these large Department of Energy X-ray sources where we bring our samples, we put them in front of the X-ray beam. Here's a diamond anvil cell, actually. So you can see I hold it in my hand. I can hold the diamond. You can see the diamond in the camera.
Oh yeah.
Looking at a quarter carat gem quality diamonds. It's epoxied. That's the black epoxy onto a tungsten carbide seat. There's another one on this side, and then the piston cylinder go together. So we'll carry 10 of these, each loaded with some material at high pressures and temperatures, and we'll carry it to the synchrotron source where we'll put it in front of the X-ray beam and then proceed to make our measurement. It's fun experiments. We're up 24 hours for 2 days, 3 days. Everybody goes so that we can take shifts. We all share each other's experiments. So we collaborate, but everybody has a lead on an experiment. So phase diagram at high pressures and temperatures, elastic properties at high pressures and temperatures, chemical reactions at high pressures and temperatures, thermal conductivity. When Emma graduates, I'll be looking for a student to take over that project. I like to have a research group that's approximately 4 people, plus or minus. It's nice. It makes sure that I know what's happening on a day-to-day level with my students. I can be a part of the project with them, but it's also enough people to have basically fun group meetings where we read papers and discuss them. And I like having a very happy group environment. Doing science is hard. There are a lot of failures. Experiments mostly don't work, and then it's confusing because by definition you're doing things that have never been done before. If it's been done before, it's not that interesting. And so we try to be a warm, accepting, welcoming community for each other.
Cool. That is great. That's something that you guys definitely want to look for when you're looking for graduate schools.
Yeah.
Because it's not that's rare. It's a lot more cutthroat in a lot of places. That sounds like a wonderful place to go.
I will tell you that every group I've been in, I've had wonderful experiences. I have, good buddy. And when you stay up all night with your colleagues, I mean, it's, it's fun. I've been in I've heard of and I've seen groups that aren't necessarily nice or respectful to each other, but there are many, many research groups that are just function at a really, really high, wonderful personal level. So, and I've been lucky to be a part of many groups like that.
Do we have any more questions? Fire away.
I have just more of a technical question. It's interesting to me that you say that you're mapping phase diagrams and just looking at what you have, it looks like it's very stable. But how do you get the chemical reaction to proceed at such time into just looking at your setup? Do you have is it 2 separate parts and allow it to come together, or I'm just interested in how that works.
Okay, so this is a simple device. The alignment, the diamonds have to be perfect. So when you're a new graduate student, one of the first things you'll do is take a piece of rock or a mineral, compress it to high pressures in the diamond cell. The first time that you take a diamond cell and put it together, it will take a week. A full time, making sure that it is perfectly aligned. After that, it only takes a day each time. So there's some time involved. Holding the sample statically at high pressures is relatively simple, but generating the high temperatures and then making sure that the X-rays go in at the same time is actually a challenging experiment. And so when we do those experiments, multiple people share control, and everything needs to be operated remotely since X-rays are dangerous, so you can't be in the same room. So since much of it is done with robotic arms that operate at micron-level precision, there's a lot of three-dimensional reasoning that has to happen. It's aided by software that's at these facilities, but the experiments can get very detailed, and you have to think quickly in some cases or wait for long periods of time in other cases. These aren't the only types of experiments I do. I have some high-temperature furnaces for running experiments. Sometimes we do a series of experiments like the ones that we were doing on liquids using a much larger volume press. We use these at the user facilities. They're more complicated to learn how to use. We do characterization of our samples afterwards. So we remove our samples from the diamond anvil cell, and that's a very tricky thing to do, and then bring them to a state-of-the-art electron microscope so that we can do a post-mortem analysis, a chemical analysis of what happened during the experiment. So there's lots of different types of analyses that we can do.
Cool. We've got another question from the National Society of Black Physicists. and you're going to have to translate this because I don't recognize the acronyms. The question is, do you just go to ALS at LBL, or do you go to other light sources like ESRF at Grenoble?
Okay, those are great questions. So the question has to do with when we use these user facilities. So these are large-scale synchrotron facilities. So for example, Argonne National Lab, the Advanced Photon Source, which is APS, it's a ring, it's a giant ring where electrons are accelerated around the ring at close to the speed of the light, and they spew X-rays tangentially all around. And then beamlines, hutches, can be built at those tangential points, and you can take your diamond anvil cell and put them in one of the hutches. Except scale it up. The circumference of the ring is a mile. Wow. So actually it's a huge facility where dozens of research groups are there simultaneously doing their experiments. So there are a few facilities on the order of a dozen state-of-the-art facilities around the world. And so the question was, what's my favorite facilities? And the answer is I go to Argonne a lot. I go to, which is the Advanced Photon Source. Berkeley is a smaller facility, but it's designed perfectly for the experiments I want to do, so that's the Advanced Light Source. There's a European facility. There's a Japanese facility. There's a series of facilities coming online. And I've never been to any of the ones outside this country, but I would love to visit.
Cool. Well, what advice would you give undergraduates in an undergraduate physics program right now, not just these students, but students that are watching the live feed, that you would say would be good advice for their future in physics and in the areas that you see as opening up in your field that are going to need researchers?
So for a physics student, I mean, such a wonderful, broad training. I would say find out early whether or not you're an experimentalist. Because if you are, you want to train. You want to get in as many different labs as possible, learn as many different vacuum systems, laser systems, optical benches, assays as you can, work in lots of different research groups to get a sense of people's styles, different ways of asking questions, different ways of designing experiments. So I think if you want to be an experimentalist, do experiments. If you're ever in a research group that's not fun, leave. There are always other research groups. So I would say for an experimentalist that. For everybody, I think the more physics courses and math courses that you take, the better. It only gets better and better. For a physicist who's interested in earth science, the barrier for geophysics is low. The science, the concepts, you've learned in your physics courses. Your mathematical tools that you'll need for doing geophysics, you already have those under your belt. So if you're interested in earth science, if you're interested in planets, if you're interested in how the earth works, if there's a part of you that's an environmentalist and wants to help society go forward as we face climate change, as we face resource management issues, then learning those concepts will come very easily to you, the earth science part of the concepts, with that basics of physics and math. So absolutely, I know at UCLA in our graduate program, we take physicists. And I didn't come from an earth science background. I came from an engineering, materials engineering background, which is similar to like a solid state physics background.
Cool. All right, John, got another question?
Yes. Listening to you talk about that, I was curious, do you have any, say, paid summer internships for graduates?
I have positions for UCLA undergraduate students. Okay. So I always have undergraduate students in my in my lab, but almost always UCLA students. Now, the National Science Foundation runs a whole series of, what are they, REUs,
Yes.
undergraduate research programs. There are many, many of them in the earth and planetary sciences. They're wonderful, wonderful programs, and I highly, and many of the students who come in to graduate school have participated in those programs. It's a great way to get research experience on board. It's a great way to travel, see a research group, go to a different city. So I highly, highly recommend those programs. They are set up to optimize the experience of undergraduates in summer programs and research labs. Yeah, that's the way I would go for those.
That's perfect. We definitely push the REU programs, and you're helping me advertise they need to go get their apps out, because
yep, absolutely.
programs are available now. Due dates are going to be in December, January. So start looking at those programs and checking it out.
There's some really wonderful ones in earth science. There's a great one in high-pressure mineral physics at the Geophysical Lab in Washington, D.C. So they're not an educational institution, they're a research institution, and one of the things they do is run a really big REU program for a summer, and lots of people in the field have been through that program. It's great. So here at UCLA, I'm the only person doing diamond cell experiments. At the Geophysical Lab, there's a dozen. So it's a big, big group, lots of people to talk to, lots of postdocs, a few graduate students, lots of research staff. It's a really, really exciting place to be.
Cool. Cool. Do we have any other questions? No? Well, let's thank our speaker one more time. This has been fantastic. I think we've set the bar now a bit higher for Google Hangouts. This is perfect with the topic level, and the background is just great. This has been a fantastic seminar, and we really appreciate your time, and hope that we can get you back again sometime.
Great. Thank you so much. This was a treat. And if anybody has any questions, please, feel free to email me or tweet.
We will.
My favorite mode of communication.
Thank you very much.
Okay, bye, everybody. So nice to meet you. Bye. Thanks.